Next up is Matthias from NVIDIA talking about a GPU-specialized inference parameter server for large-scale deep recommendation models.
Hi, my name is Matthias Langer. I'm a developer technology engineer at NVIDIA. In this talk, I will present the hierarchical parameter server, which is a central component when doing inference with our Merlin HugeCTR recommender system. This presentation will be structured as follows. First, I will discuss some basics that are relevant to understand our approach. Then I'll explain how the hierarchical parameter server works and show how it realizes online model updating. Finally, we will take a look at some experimental results. Okay, let's start with some basics. Usually, deep recommendation models consist of a DNN and one or more sparsely populated embedding tables. Embedding tables are lookup structures to turn sparse inputs into dense embedding vectors that can be consumed by the DNN. Modern recommendation systems often feature multi-giga or multi-terabyte embedding tables. Fully storing embedding tables of that size in GPU memory or other fast memories is often not possible. Also, many recommendation functions are live services that are sensitive to latency. Pre-caching could help to that end, but if the service caters to humans, the next access is inherently hard to predict. However, the overall embedding access patterns are of course not arbitrary. Access across the embedding key domain typically follows a power law distribution. That means some embeddings appear much more frequently in inference requests than others. That opens up avenues for optimization, such as caching frequent embeddings to improve latency. However, there are caveats. In live inference systems, the recall likelihood of the embeddings is in a constant flux depending on trends, fashion, disruptive events, and such. To summarize, in recommendation inference workloads, there exist structures that can be exploited, and our hierarchical parameter server, or HPS in short, does exactly that. HPS is part of NVIDIA's Merlin HugeCTR. Now, Merlin HugeCTR is a full-featured software framework for GPU-accelerated training and inference of large recommendation models. HPS is an integral part of the HugeCTR inference stack. Essentially, it is a multi-layered cache for managing embedding tables. It encompasses 3 storage layers: the persistent database, or PDB, the volatile database, or VDB, and the GPU inference embedding cache, or EIC. VDB and PDB are executed by the CPU, while the EIC is implemented in CUDA. The GPU embedding cache, or EIC, sits at the top of the HPS storage hierarchy. It uses lightweight, fine-grained synchronization mechanisms such that query and update operations can be scheduled simultaneously. Each embedding stored in the EIC occupies a slot, which is our term for triplets of key, embedding value, and access counter. Slots are organized in warps, in warp-optimized slabs. Multiple slabs then form a slab set. Embedding lookup in this cache is conducted as follows. The slab set for an embedding is determined by the key's hash value. So for each key it encounters, the GPU knows immediately which slab set it needs to search. Within the slab set, an embedding can occupy any slot. To find that slot, we lodge CUDA kernels for each slab. If a match is found, we override the access counter with the current search iteration count and return the value. If the slab set doesn't contain the key yet, the EIC automatically requests an upsearch into the least recently used slot from the next HPS layer. Now, GPU memory is too precious to be used for caching infrequently needed embeddings. To this end, we introduced 2 additional storage layers. The PDB uses persistent memory resources, such as SSD storage volumes. We use it to store a complete copy of the entire embedding table. And this replica then serves as the ground truth if searching an embedding in any of the higher storage levels fails. The VDB acts as a temporary intermediate system RAM cache to the PDB. To best utilize the available RAM, VDBs can be spread across multiple inference nodes. To achieve this, VDB database introduced the concept of partitions. That is, the underlying key space of the embedding table is split into fixed-size cache partitions that are distributed across the affiliated inference cluster nodes. During lookup, inference nodes first determine the partition for each embedding key and then reach out to the other inference nodes if necessary. now that we have covered the components, let's see how incoming inference requests are processed by our HPS. In this example, user interactions trigger some recommendation process. After determining the necessary embedding keys, the application logic first selects the available inference server and then dispatches the inference request. Now, for any sparse features encountered, the inference engine will query the HPS, which in turn will first try finding the embedding in its GPU embedding cache. If the cache hit rate exceeds some specified goal, which we call alpha here, we return the result immediately. Now, alpha is a tunable parameter to reduce latency. If the GPU cache hit rate is higher than this threshold, the response is deemed to be sufficient to meet inference KPIs, and we can immediately resume model inference without waiting for lower storage levels to respond. In any case, if embeddings were missed in the previous step, the HPS will start either a synchronous or asynchronous deep search. First in the VDB, and if it cannot satisfy the request from there, also in the PDB. To speed up future queries, deep search results are inserted into respectively the EIC and the VDB again by a background process. This way, so subsequently, as inference requests arrive, so the cache hierarchy adopts the changes in the distribution. Recommendation inevitably alters user behavior, which in turn requires model changes. Therefore, Hierarchical Parameter Server supports online model updating. During online model updating, updates from the training process are directly distributed to inference nodes with zero downtime. For example, here we have a small HugeCTR deployment with a training node on the left and a redundant inference deployment with shared VDB on the right. The training node can directly publish its model updates via our producer API. The producer API will automatically organize, sort, and batch the updates and deliver them into a Kafka message queue. Via our consumer API, each node with VDB or PDB can automatically discover and ingest compatible Kafka message queue updates. If a VDB is shared, like in this example by multiple inference nodes, the update workload is also split among them. So there's no double work happening here. As updates are processed, the Kafka subscription status is of course conservatively incremented, and so eventually we can, with this approach, we can guarantee final consistency. Last but not least, the EIC needs to be updated. To limit the amount of interruption of the inference process and the interruption of the GPU, we implement an iterative polling-based mechanism there, where the EIC subsequently queries the lower storage levels for updates and downloads them. EIC polling cycles are triggered either repeatedly by timer events or if NVIDIA Triton signals that a major update is available. Next, let's have a look at some actual performance figures. So here we investigate how a single HPS instance fares against a PyTorch CPU implementation. To that end, we respectively plotted the latency and the throughput when doing inference with a DLRM model at different batch sizes on a single DGX A100 node. As dataset, we used the Criteo 1 terabyte click log. This machine that we used here has 2 terabytes of CPU memory, which is enough to cache the entire 90 gigabyte embedding table in CPU memory. PyTorch uses only the CPU memory to recall embeddings, whereas the HPS utilizes its EIC to cache up to 50% of the embeddings in GPU memory. As can be seen, the high GPU memory bandwidth allows HPS to retain a much higher overall inference request throughput. Due to its early return mechanism, HPS latency remains low across the board. Meanwhile, PyTorch latency figures explode, and that is because looking up all these embeddings that are maybe not needed a lot really takes a lot of time and just like delays further processing. We can also, next we rerun the HPS part of this experiment with a similar but larger embedding table that measures 650 gigabyte. Due to the increased embedding size, we reduced the EIC's cache ratio to 5%, so 32.5 gigabyte are cached in the GPU. Unsurprisingly, the throughput increases as the batch size increases. We can reach nearly the same throughput as with the smaller criteria 1 terabyte data model. Inference latency remains low despite the much larger model size, and that is because of this early return mechanism. Again, so having sufficient memory to cache the entire embedding tables is not a typical scenario in large-scale inference. Here we demonstrate the influence of different HPS configurations. I will discuss this bar chart from the right to the left, so you can easily follow me. So the purple configuration uses no intermediate system RAM cache. The poor performance is a result of the severe latency deviation between GPUs and SSD hard disks. This is opposed by the green and yellow configurations, which have sufficient memory to cache the entire embedding table. The blue and orange configurations use cross-machine RAM to cache large portions, but not all embeddings. Despite the limited memory usage, they achieve a comparatively high throughput. Note how carefully balancing the cache rates between EIC and VDP leads to different results. In this example, they are caching 5% more embeddings in the Redis VDP, improves throughput much more than doubling the size of the GPU embedding cache. We can also repeat this experiment with the larger 650 gigabyte embedding table. Again, note how permitting the VDP to use 5% more memory for caching frequent embeddings significantly boosts the overall throughput. HPS doesn't require high-end GPUs to perform well. On the left, we provide DLRM inference latency figures for respectively an NVIDIA Tesla T4, A30, and A100 GPU. We limited the EIC's cache rate to 10% in this experiment, so that the A100s and A30s increased memory size doesn't provide any advantage here. As can be seen, the latency differences between these GPUs are largely neglectable. Only for the very large model batch sizes, the increased memory bandwidth and increased amount of CUDA cores of the A100 and A30 GPUs really becomes beneficial. This concludes my presentation of our HugeCTR Hierarchical Parameter Server. Please have a look at our paper for additional insights, analysis, and benchmark results. There's quite a few that I didn't cover here. HugeCTR is available for free on GitHub. And yeah, thank you for your attention.
Awesome, thank you. Bunch of questions in here too. Most upvoted one so far. What are the key factors on deciding whether to serve through CPU versus GPU?
The key factors. Well, normally you are executing all the deep learning code in the GPU. So naturally, you want to have your embeddings readily available when you need them for lookup to not delay downstream processing. So there is actually not, if your model is processed on the GPU, you want the embeddings in the GPU, as many as possible. And if you are processing in the CPU, then in the CPU. And any piece of more cache helps, always in these. But of course, with diminishing returns because of the power law distribution.
Great. Next question. Have you considered sharing embedding across GPU HBMs? The
embedding inference cache is actually can be shared by multiple processors. So all transactions on the EIC are atomic, use synchronization primitives that ensure that the updates are everything is thread safe. So you can use two processes and use exactly the same embedding cache.
Great. Have you looked at the distribution of latencies for inference of different users, such as those with more niche taste?
Well, that is then now more an application issue. Well, this is no. This is what application issue. I mean, we are providing the tool. We are not. Our customers probably do that. Yes.
Okay. Let's see. How do you handle the orchestration synchronization between nodes? Do you use a message broker or messaging? Yeah, I think it's message broker. What about a caching mechanism?
don't exactly understand the question. We use Kafka for the updates as an intermediate storage, and with Kafka we can have offset markers, so we know exactly the read offset of each worker and each partition. So each partition, we know exactly which updates have been consumed and which have not been consumed. And once they are all in sync and are at the end of the Kafka message broker, then we know also all models have been updated.
Great.
Yeah.
Great. Let's thank Matthias again. All right. Now it's time.